Yeah, so I'm very glad to be hosting the talk today. I'm Estelle. I'm a student at UCL, and I'm very glad to introduce Ingo here. Dr. Ingo Waldmann is an associate professor at UCL and University College London, and the deputy director of the Center for Space Exochemistry Data. He is the PI of the Exo AI group, which focuses on developing and implementing AI data analysis and modeling solutions to exoplanet characterization. And he's also the data analysis lead for the middle-class ESA aerial mission due to launch in 2029 now, I think. So yeah, Ingo, the Zoom floor is all yours.
Brilliant. Thanks very much for having me. It's a pleasure. And thanks for the introduction. That was great. I already just told Estelle that there might be some background noise. We just got a dog from the pound on Sunday, a rescue dog, and she's a bit barky. And we've got some builders in there who are supposed to have finished, but one of them broke his foot, so they're a bit delayed. So really sorry if, I hope you can hear me throughout. Well, so thanks very much. Obviously not talking about my own research because all I get to do is answer emails all the time. But that of some of my PhD students and postdocs, especially here Kai Yip and Maria Morvin, so the part of the Exo AI team, and we're basically this team's been set up to start developing machine learning and deep learning solutions to exoplanet data analysis. So it's time series modeling as well as characterization, so atmospheric retrievals. So I'll talk about those two. But we've also then further branched out recently into general characterization of the ESA data archives of David Smith. So there's an ESA shared project. And we have a couple of students, Max and George and David to a degree, working on Mars and Venus data. So there's quite a lot of stuff to do with planetary science and exoplanets. With machine learning, it's all still very, very new, and we're relatively far behind compared to, say, cosmologists who've been using AI techniques for quite some time. So yeah. Let's get started. So planetary atmospheres, you of course know what planetary atmospheres are, and you obviously know what exoplanets are, so I'm not going to really introduce them very much. But studying the atmosphere of an exoplanet will tell you a lot about that foreign world. And this is an illustration hand-drawn by my own hands on my iPad. And what it can show you is by studying the chemical signatures and the cloud formation signatures of the exoplanet atmosphere, it can show you or give you insight into the formation history through the carbon to oxygen ratio and the metallicity of the atmosphere, for example. It can show whether there have been any recent impacts. So there have been a couple of papers on terrestrial atmospheres as well as gaseous atmospheres. Whether there's disequilibrium driven from outside. We've, as you know, obviously mapped quite a few hot Jupiters now. We see some cloud coverage in some of them, and in some of the warm Neptune Studio 1214b being one of them, it seems to be entirely cloudy. So we can see clouds with Hubble Space Telescope, and with James Webb Space Telescope, we will be able to characterize even the composition of these clouds, hopefully. Then the impact of stellar radiations. A lot of these hot Jupiters, are very close to their host stars. They're basically inside the stellar atmosphere. So that obviously has a very strong impact that we can measure through the chemistry, the photo ionization of the upper atmosphere, for example. Escape mechanisms are important. Volcanism for terrestrial planets. And what the media cares for is, are there aliens or not? Right. So through disequilibrium chemistry and biomarkers and so on and so forth. Now that's all fair and good, but to get there, we need to really look at a lot of subfields. And this exoplanets in itself is a very interdisciplinary field, and it doesn't really fit one individual box, which makes this so exciting. So we need to really have detection people collaborate with data analysis, so pure observers with data analysts in time series and so on and so forth. Atmospheric modeling, and once we've then learned lessons from the data that we have and the instruments that we used, we then go back in a loop and try to improve on instrumentation by building new dedicated instruments like the Aerial Space Mission, for example, or Twinkle, but also James Webb and the calibration for the James Webb Space Instrument. So it's it really encompasses all aspects of astronomy in one field. Oh, a lot of them anyways. Right, so instead of being able to talk about all of them in the seminar, I'm just going to do 2 of them, and I'll just give you a quick update sort of what we've done recently in these areas. So data analysis being the first one. To give you a bit of an introduction to transiting exoplanets, of course you know that, but it's always good to have a slide on what a transit is. So this is the transit of Venus in front of our own star, and as the planet passes in front of the star, it obscures some of the light. Now that gives you a light curve, as you see, which is in this case quite clean. There's no autocorrelated noise, but we'll get to that in a moment. But what happens if the planet has an atmosphere? Then the very thin annulus of the atmosphere filters some of the star's light. So this is of the order of, 20, 30 to sometimes 100 ppm of the stellar light goes through the atmosphere, through the terminator, and you can see the absorption features of the atmospheric chemistry in that light. So that's all very good and all very easy. So I'll have a first go at Mari Morgan's recent work, which is analyzing some of the legacy Spitzer data. Spitzer has been extremely important in exoplanet spectroscopy, continues to be for quite a lot of planets, though it is defunct now. But the data is still very relevant because it was the only mission until James Webb to really provide us data in the infrared around 3.6, 4.5, and 8 micron. But what you can see here, this is a typical example. I don't know if you can see my cursor. Typical example of Spitzer data. So from Heather Knudsen's paper and then Jean-Philippe Bioleu's paper, and they had a bit of a forth and back on these data sets and how to analyze these data sets, because these are very, very correlated observations. You can here see in the 8 micron channels, it's relatively clean, and the out of transit data here is very, has a bit of a trend, but it's more of a second order polynomial or linear trend. But then in the 3.6 micron channel and the MCD detectors, you see something very, very different and very, very strong systematic noise. And this is in Spitzer, it's due to inter and intra-pixel variation. So the quantum efficiency of the individual pixel is changing as you scan your point spread function across the pixel, because there's an intrinsic jitter with Spitzer, the Spitzer Space Telescope. So the quantum efficiency is nonlinear, as well as the overall field. So individual pixels have different responses. So that combined gives you a very, very strong correlated noise across your time series. And having to correct for that is rather tricky. And you can see that your correction is of the order of the sine signal, sometimes orders of magnitude higher. Sorry for the building noise. And here in the secondary eclipse case, you can barely see the eclipse here. The noise is so strong. Now, way back now, 10 years ago, a lot of these approaches were parametric, and they were basically due to how an individual group defined their correction algorithm or model. And that led to quite a lot of issues and quite a lot of controversies, because different groups had different interpretations of how to treat this noise. That was then partially solved by a couple of non-parametric algorithms, for example, Gaussian processes up here, pixel mapping here, and independent component analysis. And in 2016, the Spitzer Data Challenge was held, where they, the telescope basically made artificial data on which to test these new algorithms. The data challenge here, we won with our ICA approach, independent component analysis, which was deemed to be the most reliable and repeatable. Didn't get any prize or anything. We just got this one graph and one single mention. But it was still very nice to do the data challenge, and we were still very happy. And it turned out that a lot of the earlier controversies using Gaussian processes or ICA or any of these other methods could be resolved by using a purely statistical approach rather than a user-defined model to detect the data. Now we thought that this is all great. Can we take this a bit further? And there's been since 2016, there's been obviously the rise of deep learning and convolutional and time-dependent networks. And we thought an independent component analysis can be understood as a single layer feed-forward neural network. It's basically the same, but we can actually only capture linear trends with an independent component analysis. While with a deep neural network, they're very, very good at capturing very nonlinear trends, as you know. So they've been used in a lot of fields in industry and science now, and we thought, why not try as well? Now the issue is with a normal feed-forward network here. This is just a very simple idea. Is that they don't have an intrinsic time component to it. So you can use a normal deep belief network or convolutional neural net and model a time series very well, but there is no understanding of it's time agnostic. So you can't use it to forecast necessarily into new time regimes. So you can't train it on one time slot and then expect it to do well on another time slot. It doesn't have this time-dependent autocorrelation. So we thought, we can easily address that by using a recursive neural network. So the long short-term memory network is the most standard one in deep learning. Gated recurrent units are also now coming up, which I can talk about later. But very oversimplified, the idea is that here from time t-1 to t+2, so this is a time series down here as input, the neural network basically propagates information across its layers in time, so it can start learning time dependence. Now, I'm not going to necessarily go into the internal setup of an LSTM cell, but have a look down here in this block. It's quite a long URL, but it's definitely worth looking at because it's a very nice description of what an LSTM cell is. But the idea is that from a previous time state to the next time state, it can forget where you can retain or forget information that it had before. And this is better compared to a classical recurrence cell, because you don't have a vanishing gradient problem anymore. It basically can identify important features in its time sequence and retain that information whilst deleting other unnecessary information. And that's been used across many fields, but especially across industry. And we came across this paper from Amazon. And when you come across a paper from Amazon, you should pay attention, because it's usually, they know what they're doing. They've got a working business model, as we all know, and it's called deep autoregressive probabilistic forecasting. And what Amazon does to set a price point of an individual product is not to just forecast the individual product in time, given its sales performance in the past, but what it will do, it will forecast all products that it offers globally including all sorts of other auxiliary data, weather patterns in the individual country, stock exchange figures, whatever not. And the interesting thing about their forecasting technique is that these individual time series don't need to be uniformly sampled. They don't even need to be on the same time grid. So you can basically throw anything as long as it's some sort of time series into this model, and it can help forecast probabilistically the sale price of an individual or the demand of an individual product. So this is one of the first applications where this has been really used to model hundreds of thousands of data points or time series points simultaneously. So we thought that might be quite interesting because we have a similar issue. We have a lot of auxiliary information quite often, for example, temperature sensors, pointing information, and so on and so forth, but they're quite often not sampled with the same cadence as the science data. So using a model like this will actually give us quite a lot of advantages. So what we've basically done, if we've built on this and built a deep Lstm model, so instead of a single layer, as I showed you before, we're doing this 3 times. So basically a time-dependent neural network stacked on top of another, which then outputs a probability distribution, a mean and a sigma around the mean. So it's a probabilistic forecast, deep probabilistic forecaster. I'm not going to go into the details here, but basically what we do is then we train it on the raw data. Here on the left is the blue curve. We give it a learning range, and the range is obviously very important because the longer the range, the lower the frequencies, the lower harmonics it can pick up, right? So if you have a smaller range, all it can see really is high frequency noise, whilst if you have a longer range, obviously you can see these stronger sinusoidal features here. And we train it on different time lags and time steps, and then we make it forecast in a prediction range, and then we iterate over that until the prediction becomes as good as the trained data. So we test it on this red region here and train it on the green region until it's converged. And then we start forecasting across the exoplanet transit. We don't want to include the transit photometry in itself, because that may be able to, the network could overlearn, right? It could just memorize the shape of the transit, and that's not what we want. We want to not learn the transit, but we want to learn the systematic model of the systematic noise of the telescope. So here, basically, the autocorrelated time series signal. We also feed in auxiliary information such as the X position and the Y position of the point spread function on the detector. As you can see, this is strongly correlated, so it's useful information that we can obtain easily without having to model the transit feature. And then basically we predict forward. So this is an example of the training data here, where on the left and right of these dotted lines, we use that as training data, and then we predict the in-between. So this has obviously no transit in here. This is just out of transit data, but the idea was, can we actually predict the real data is the blue, and the orange is the predicted time series. So it looks very, very promising, and we're basically getting a lot of the features, lower frequencies as well as high frequencies. So that was very, very good. And then we basically, so exactly. So the green is the training, and then the red is the prediction. And then we've applied it to, so this is for an individual time series only. So, and then we've applied that to a very well-known data set, the HD29458 training set by Eric Agel, data set by Eric Agel, where we have 6 very good time series here, but all of them having quite different systematics, as you can see. Yeah, and here down in the red is our Lstm prediction. So it really captures individual time series issues here and predicts them very well. Now, we can train the neural network on an individual time series. We can train it on multiple time series. And so this is actually useful in multiple aspects. You can, for example, if you have a spectrometer, for example, a James Webb time series will have wavelength information, right? So you have wavelength resolved time series that you can feed in to this Lstm for it to model not only the time dependence, but also the wavelength dependent systematics. You could use this for test data or Kepler data. So this is what we're currently working on, to feed in all of the stellar time series simultaneously and then learn the common underlying behavior of the instrument, right? Because the instrument and the systematics of the star are, convolved with individual individual stars, but there might be an underlying function. So this is similar to the Kepler data analysis and the test data analysis, because you get these underlying PCA components that you can take out, but PCA is obviously just a linear component, whilst an Lstm actually can give you a nonlinear solution. So what you do here, if you then take the prediction and subtract it from the real data, you get this very clean light curve out, which is good. And if you look at, compare that to the original paper by Eric Agel, we can see that it's similar, but ours has slightly less variance in, the different observations. So the observations agree somewhat slightly more with each other than the original parametric solution, which is good. So basically, there's been a lot of debate with these data sets whether there's an aspect of stellar variability, and there probably is, or planetary variability, but a lot of these variabilities are due to the way you reduce the data. Right. Yeah, let's go to the atmospheric modeling. So once we've got a spectrum out of our time series data, we need to model it with an atmospheric forward model. So in the past, say 10 years ago or so, all people did really is have an atmospheric model, had a few parameters, and then did a forward model and then overplotted that with the data. But of course, that's not what's happening right now anymore, but we go backwards, and it's called atmospheric retrieval, where we solve the inverse process and we go from the data to the probability distribution of the model parameters. So retrievals are basically just a fancy way of saying that we're fitting the data. And that data is becoming more and more complex, and the models are becoming more and more complex. And with James Webb, this is going to be particularly true, where we can't rely on the simple assumptions of isothermal temperatures in transmission, for example, for hot Jupiters. What we've done so far with HST data, James Webb won't allow us to do that. So we have to really model very complex chemistries, disequilibrium chemistry, photochemistry, and all sorts of other condensation processes and 3D effects. And these atmospheric forward models then become very, very, very slow and almost impossible to run with a normal Markov chain Monte Carlo fitting. Yeah, there's quite a lot of work being done at the moment with atmospheric retrievals, and I do apologize if I don't have your favorite retrieval code in this list. Please just tell me and I'll add it. There are quite a few coming out now or being having been published recently. It's quite a cottage industry now, and the idea is here that we solve the posterior distribution of our Bayesian argument. And in this case, for example, you can see this is just for hot Jupiter. These can be quite complex. And this is just for a very simple model of water, CO, CH4, isothermal temperature, radius of the planet. a simple cloud layer. But as we go forward with James Webb, we have to have very complex models, and these parameter dimensions going to be very, very large. That is something that cosmologists usually deal with. Is something that we have to now tackle as well. And on top of that, some of the input data is going to be humongous. Line lists, for example, molecular line lists, ab initio line lists from high temp and ExoMol, for example, they can easily be several gigabytes to terabytes if we want to model it in high resolution. So running these models becomes very, very tricky. Not impossible, but tricky. So we thought back, this is the dark ages of deep learning. This is before TensorFlow was a thing. So the model was written in Theano, which is not something I would ever recommend to anyone. We thought like, okay, well, can we use a neural network, for example, to at least help this process somewhat? And back in the day, it was a pure qualitative method and trying to see whether, a neural network, in this case, a very simple deep belief network, could identify qualitatively whether a molecule is present in an atmosphere or in a spectrum, so that we can include it into an atmospheric retrieval and don't have to include all of the molecules that we have, because that's quite often infeasible. So it turns out it's really, really, really simple to do that. It works really well. It's quite an easy task for a neural network to do. Even if you have mixtures of molecules in here, it predicts it very, very well. So that was 2016. That was super long ago. Back in the day, start of deep learning, basically, or in science, that was a very early on, and the Daily Mail picked up on it for some reason. And instead of being a bit, in the UK, the Daily Mail is, since this is being recorded, I'm going to be polite. It's a tabloid with well, factually questionable content at times, but they came up with we called our model Robert, robotic analysis of exoplanet something, and they basically came up with AI hunting for aliens. And the way they illustrated that quite clearly is with this illustration, which I thought was just amazing. A sentient humanoid robot looking at analog stacks of files. So that's exactly how a robot works, and I'm not going to even go into any further detail. Yeah, but the field fortunately has moved on from then, and quite a bit. So deep learning in exoplanets is actually quite a growing cottage industry, which is great. And in the last 3 years or so, we've seen about 60 papers using some sort of AI mechanism or machine learning mechanism to detrend data or analyze data, which is great. We're still very, very far behind other fields like cosmology, but it's really, really, picking up now. Most of these methods are for planet detection using TESS and Kepler. A few of them are now coming up for characterization as well. So this is an interesting one. This is from this year, Hims et al. 2021. And instead of using a neural network, which is basically a pretty black box quite often, and we're not quite sure whether it converged or not, to go the full way from a spectrum to the parameter, they used a neural network as a surrogate model for the radiative transfer, and then basically plugged it into a standard Markov chain Monte Carlo algorithm, and just went on with the retrieval as they otherwise would. And it seems to work really, really well. And you can see the predicted and the true spectra here are very good and very much overlapping. So that's one approach, and it's an approach that's also been used now relatively often in retrievals of Earth atmospheres. So in the Earth community, using surrogate models or surrogate radiative transfer models is becoming relatively common now. So yeah, that's great. In 2018, our group did use something different, because a generative adversarial network. It's basically where you try to solve the full thing. And the good thing about GANs is that they're likelihood-free models. You don't have to give any assumptions about the underlying likelihood of the data or the model, which is quite good, because let's be frank, we don't know what the likelihood really is of these retrieval models. Rather than going into the GAN generally, I'm going to have a look at the paper. There's another paper by Cobb et al. 2019, and who used an ensemble neural network, which also worked really well. The issue is these come up with quite often the right solution. The issue is that they don't have formally include the error on the data. They have an error on the prediction within the neural network, so it can propagate that, but it can't include the error on the data itself. So it's not formally Bayesian at the moment. That's one issue. The other issue is quite often that, definitely for GAN, they are quite black boxy. So you're not 100% sure whether they're fully converged, or what they converge to, or what they've actually learned. And that becomes a problem. Different approach, again, by the Bern group and the Cambridge group, is to not use deep learning at all, but go for more classical random forests, which are far more explainable. You can really trace decision making in a random forest quite easily, which is great. The drawback here is that they are not as easy to generalize to unseen spectra. So you have to often retrain for an individual spectrum, which, you know, doesn't defeat the point, but it makes it harder to apply. Yeah, but do check out these papers, they're very good. So, you know, I've already mentioned it. There's not only one elephant in the room. There are several elephants. There's a herd of elephants, and that's quite hard to control. And you know, we don't really know how neural networks learn. There's been done quite a lot of theoretical work on this, but we don't know whether they actually learn the astrophysics if it's presented through training data, or whether it's just learning some sort of, you know, over-interpreting the data by just, you know, memorizing solutions. So we don't know whether they learn. We don't know what exactly they learn. We don't really, until now, really understand how biased their solutions are, their outputs, and the uncertainty of the neural network in itself has not really been addressed so much in most of these papers. And, you know, we need to address all of these if we really want to be able to use these in production and actually have a broader adoption of neural networks in the field. And I think one of the hinging factors in adopting deep learning approaches in retrievals is this black box behavior. Right, so it's not only a problem for us, it's a problem generally, and it's a problem for basically the physical sciences, and is so driven by the need to explain the decision making of a neural network in the physical sciences. It was that was the starting point for what's called explainable AI, which is this subfield of deep learning, just, you know, very, very fast moving. And the idea is to really break this degeneracy and break this black box behavior, and being able to explain why it makes decisions and how confident it is. So I don't really have time to, you know, discuss this in detail, but please do, if you're interested, please do read this paper down here. It's hideously long and dense, but it gives you a fantastic overview of what's been done at the moment in explainable AI. And that's from the paper. And there are multiple ways of, you know, going about this. For us, you know, the easiest ways are a local explanation. So what happens if a prediction Y, for example, water content of an atmosphere, if we change slightly the feature of X, Y, so a feature in the spectrum. So if we perturb something in the input, how does that affect the output, if at all? That's local explanations. That's, it's kind of like a jackknife Monte Carlo. Feature relevance. Feature X has a 90% importance in Y. So how important is a feature in the input to determine the solution in the output? Again, quite similar. And visualization. I think this is probably one of the easiest as well, so especially with a variational autoencoder, where you translate an input into a latent variable space. So basically a compressed representation. You can think of it as a nonlinear principal component vector. And you can plot that quite easily. You can cluster that and see whether there are distinct solutions learned by the neural network, whether the neural network has learned to differentiate cases. If it has, great, then you can analyze that and pick out individual points and individual clusters and see what that means. So latent variable presentations are quite good. Model simplifications, text explanations, and so on and so forth, also there, but not so relevant to us. Right, so then we went on and had a look at what we can do in terms of breaking this black box behavior. So this is Gordon Yip's work, which is on arXiv and is hopefully about to be accepted. I mean, we had the referee report back, which is great, and yeah, and resubmitting that next week probably. What we did in that paper is a couple of things, and one of the things is that we really wanted to understand whether there's a preferred architecture of neural networks for this sort of work, because including ourselves, everyone blames each other for using the wrong architecture, or says that is convinced that their approach is the best. I mean, we've said this in our papers, and other people have said this in their papers. So we had a look at different architectures across the board, whether it actually makes a difference. The answer is no, it doesn't at all. So that's surprising, but great. So we looked at a very simple multi-layer perceptron, so a deep belief network, most simplest form. We looked at convolutional neural network architectures, and we looked at long short-term memory architectures, right? So modeling basically the spectrum as a time series, because you can just think of it as being a correlated set of points. It doesn't make a difference. Most of them work pretty well, and with some hyperparameter optimization, you can make all of them pretty similar. Now we used simulations from the ESA aerial mission, simply because we've got the mission simulator being very close to aerial, but this also applies to James Webb, and we will have a James Webb follow-up on this as well. Right, so on the right hand side, you can see this plot. You can, if you read one of these papers, generally this is sort of a plot that you quite often see, where you have predicted abundance, for example, on your y-axis, and then the true abundance on your x-axis. And the neural network should be on the diagonal. These predictions should be on the diagonal, which in most cases it is. And then at some stage, the abundances get too low. It doesn't really know what to do, and it veers off. Fine, great. That's useful to know, but it doesn't actually show us the full picture, because as you can already see in these diagrams, is that the sampling is not uniform. And so there's quite a lot of structure inside. So you can plot that differently, and then you already see quite a different picture. So this is where we now look at the average deviation from the expected and the true abundance. So here we have a 10 to the minus 4, for example, input abundance of water in the input spectrum, here 10 to the minus 8, 10 to the minus 7 here. And the prediction is basically the true minus predicted, the deviation here. And what's interesting to see is it was initially a little unexpected, but it does make sense that if you have a spectrum that is very, has very clear water features, it will very clearly find water features because it has a feature to look at. It can see water and then can classify water. But as the water diminishes, it becomes less certain, but it also becomes more biased because it can't really, it gets confused, for example, with other spectral features like methane or so. So it starts over predicting. But then if water completely disappears and there's no trace of it and the spectra becomes quite flat because there's no water, for example, it is very certain that there's no water. But interestingly enough, it doesn't care whether it's 10 to the minus 7 or 10 to the minus 15. It just chooses a number. It's easier for the neural network to just have a single data point that says no water rather than giving you a lower limit. And then it starts increasing again, and then the bias starts increasing again. And this is an edge effect of the training data, we think. So if you curtail this in terms of if you stop this at 10 to the minus 8, this entire behavior starts compressing. So it's important how you build your training data, and it's important to understand what it actually means as an output, because it goes the lazy way quite often, and if it says no water, it says 10 to the minus 7 water instead of giving you a range as expected. CO here is another case. This is expected because the CO is really not observable or very hard to observe with aerial. So it's quite uncertain overall, and then it finds a no CO solution where it's absolutely sure that it's not there, and then it doesn't care anymore. Yeah, so it's interesting. So you can then express this into different charts. Here on the left, we again look at the deviation. So basically the bias of the network, and it starts and as expected, the solution becomes more biased the harder it gets. So the better the input spectrum, the more certain and close to the real thing it is. But then the harder it gets, the more biased it becomes. And the other line, the black line here, is the frequency of predictions, and you can see that again it has a preferred area of predicting. So if there's no water, it's definitely will put it down to 10 to the minus 7 or so. So it's not a uniform output, and this is important to understand, and this is important to know if you ever want to trust these systems, because there's clearly morphology in the way it does things. You can translate that into a probability of water being in the spectrum, and then here we just set a random threshold at 70%. That's just randomly picked. But if we take that, then anything down to 10 to the minus 4, 10 to the minus 5, perhaps in water is okay for the neural network. With CH4, it's a bit lower. So you can set these probability thresholds on where you should trust your network and where it starts becoming a little bit iffy. Now, then we thought, okay, well, so what happens? So there are clearly biases and there are clearly things going on. What happens if we give it more data, a bigger training set, and what happens if we make the model more complex? So that was also quite surprising, but again, it does make sense if you think about it. If you give it more data, it obviously becomes a little bit better, but not by much. But if you give it, if you make it more complex and give it more data, there's hardly any improvement over a simple model with less data. So basically, what happens is that if you give it, a more complex model will have a lower have a lower bias. It will be able to map nonlinearities in your atmospheric model better because it has more capacity to do so. But the trade-off is that the extra amount of layers and neurons inside the neural network, because they're all Gaussian activated, will induce more noise. And if you give an infinite amount of data, then yes, it will converge to a good solution, but that's not usually the case. So the bias will go down, but the error bar will go up. And it's quite intriguing to see that you can actually use a simpler model, which will be more biased, but it'll be more certain of itself in a sense. So it's these, here you can see these error bars are all overlapping. There's no real gain in trying to make a model too complex. So what you can do, for example, something we haven't done yet, and we will investigate in future papers, is to go from a complex model and then start pruning it down to a sparse representation. So there's quite a lot of work done on sparsity in deep nets and how that improves bias and uncertainties inside networks. But for now, simple takeaway here is like going more complex doesn't necessarily solve the issue. But then we thought, okay, finally, okay, so we understand the biases now, and we understand that there's uncertainty, but does it actually capture any of the physics? And yeah, I'm nearly done. So does it capture any of the physics at all, or is it just literally learning the training data and making decisions that don't make sense from a physics point of view? And we were very pleasantly surprised that that isn't the case, and it actually understands what it's looking at. So that's really promising. So for example, here for a carbon monoxide feature, it's here. So the colors are the activations. So the sensitivity of the point to the abundance measure that the neural network predicts. And so the brighter the color, the more important the points are for the output of the neural network. And you can see here for carbon monoxide, it picks up the carbon monoxide features, and it neglects the smallest one and goes for the big chunky ones, which is kind of what we expect. This is what an observer would do. Then for methane, it's more complicated because methane is obviously a much broader absorber, because the methane bands are pretty much continuous throughout here. And it doesn't go for every methane feature, but it goes for the new free band at 3.1 microns. And it's the strongest band, but it's also, interestingly enough, if you look here on the right-hand side, it's one of the only bands that isn't contaminated by other molecules that are overlapping, or the least contaminated. So it's understanding that these points are the least biased estimators of methane in the spectrum, and it puts most of its weight onto that, and a little bit of weight onto the rest of the spectrum. Then for features that are don't have any intrinsic spectral features themselves, for example, clouds. In this case, we have just used an opaque cloud layer, which will just cut off the bottom of the spectrum, and there it really does something interesting as well. It looks at the only point here in the area that is sensitive on the left to the Rayleigh scattering curve, looks whether it's there or whether it's cut off by clouds, looks at the deepest point in the atmosphere, which is the point to the right of that, and then looks at the highest point of the atmosphere given the spectrum. So it's measuring the scale height, and it's measuring how deep it goes, and if there's a Rayleigh curve. If there's no Rayleigh curve, there's clouds. If these points are cut off, they're clouds as well. So it makes sense. This is, if you're a spectroscopist and you're looking at a spectrum before you're doing your retrieval, you can already sort of guesstimate what's going to happen based from experience from just looking at it. And the neural network basically does the same thing, and it does it quite well. Temperature, similar thing. It tries to estimate, or it looks like it's trying to estimate the extent of the atmosphere by looking at the Rayleigh curve on the left and the scatter of points along here. So it becomes more complex, but it's doing stuff. Anyways, so that's really promising. And yeah, and it basically shows us that we can take this further, because it actually makes sense to take it further, because it learns physics by example. Otherwise, if that wouldn't be the case, what's the point, really? Anyways, something completely different. So Ariel needs you, and we're currently running a machine learning challenge. So we ran one in 2019 as part of the European Conference for Machine Learning. It's one of the largest machine learning conferences in the world each year. And in this case, this year, we're running it on detecting crossings, planet crossings across sunspots and faculae. So basically contaminated light curves in low signal to noise measurements. And yeah, because you've seen what happens if you don't detrend it properly from before. And with low signal to noise data, that will be an issue. So yeah, we thought it might be interesting to look at new solutions by inviting the machine learning community and whoever else wants to participate. So last time we had about 110 participants across industry, AI, and astrophysics, and this year we have about, I think, 94 today who are participating. So have a look at the data challenge. It is a lot of fun, hopefully, and if fun isn't good enough for you, then you get 500 euros or the cost of ECML registration at the end of it if you're one of the top 2 contenders. Yeah, so here's a QR code that you can scan or have a look on the website, and all the information should be there. Otherwise, just send me an email. And yeah, that's me done. And yeah, these are conclusions. Basically, machine learning is coming up very rapidly in multiple fields in exoplanets. Explainable AI will be useful to break some of the skepticism in the field to black box models, because they're not really black box anymore. You can interrogate them. And yeah, participate to the data challenge. That's it. Thanks very much.
Thank you very much, Ingo. So I don't see any questions in the chat, but feel free to post them or to raise your hand and then unmute yourself. In the meantime, so I will let the time for people to gather questions. But yeah, I do have a question. It's not a very technical one, but you did mention that so JWST is coming. I mean, it's going to be launched soon, hopefully. And so what do you think is hindering, will be hindering us when JWST is launched in terms of atmospheric retrievals? Is it like, for example, among the elements that you mentioned, like what do you think is, can you identify something that we could work on?
Oh my God.
Yeah.
Well, so yeah, I should tread carefully here, but I think it's fair to say that James Webb will deliver such incredible data with such signal to noise and resolution that we don't even understand what to do with it at this point, at least from a modeling perspective. I think there are to quote one of your infamous politicians as the unknowns. And the known unknowns, and then the unknown unknowns. And I'm not sure whether we really understand how many unknown unknowns there are at the moment. The modeling will, I think, go through, we will get these fantastic spectra through early release science and the GTO, and then the GEO proposals. And I think that it will be an iteration of papers before we get to what we perceive to be the ground truth. In this, because we've had Hubble with one, a micron basically of wavelength coverage, and now we have James Webb coming up with a massive resolution, super signal to noise, and 1 to 10 microns in transmission, and it's just going to blow our minds. And I don't really think that we have the models available right now to, at least on the retrieval side, to really cope with that very effectively. there are a lot of groups doing a lot of amazing work at the moment, and going from 1D models to 2D and 3D models now on the chemistry side, but it needs to still all fit together, and how that's going to work. And then to understand what we're still missing is going to be an interesting question.
Okay. Do you think that
can I ask a
JWST
question?
that? Oh, yeah, sorry. Go.
Yes, hi, this is Leon Hoffman speaking. I have a good question. When you talk about self-calibrating approaches, do you basically mean unsupervised learning, or is it
Yes.
supervised?
Either. So you can, in this case, it's for the time series, for example, was supervised learning because we just use the out of transit data, but yet you can use unsupervised learning. So one way of using unsupervised methods that's come up quite a lot in galaxy classification is contrastive learning, where you're trying to cluster different different models with each other and then trying to learn from one another. So it's like student-teacher approach. Yeah, but here, what in this talk specifically, it was just supervised. But from the data.
Yeah. Okay.
Not...
Thank you. Because I thought that unsupervised would be better, sort of, to uncover unknown unknowns than the supervised.
Yeah. I just don't know how to do it. I mean, if anyone does, then yeah, that'd be great discussion to have. Yes. Ideally, we want a system that tells us what complexity is required in our atmospheric model to model a spectrum like that. We want to look at the information entropy of a spectrum rather than the model in itself. How one does that, I don't know.
Joe?
Thank you.
Hi, yeah, great talk. I was really curious if you could talk any more about just the transit light curve learning, specifically related to, can you pull out multiple planets? Like if there was a multi-planet system and one of them was hidden inside the light curve, have you done any work looking at that?
We've started looking at that, actually. Still very early stages, though. If you have a long enough time series, it should be fine, because it should wash out in the Lstm. It really depends. I think it was going to be very case dependent on how autocorrelated the star is. Yeah. But it's something that can definitely be trained, even with a semi-supervised system. So another paper that Mario, which I should have mentioned, has recently published, is a PyTorch version of a transit light curve. So you can fully add the transit, the Mandel and Nagel light curve, or in our case it's PyTorch, into your neural network. So that basically adds a physical constraint to your neural network. So it can focus more on modeling non-light curve features rather than. So you don't have to exclude the light curve anymore to make sure that you're not modeling the light curve. You just put the light curve model in. You have two strands in the neural net, one a light curve strand and a systematic feature strand, and then you combine them in the top, or you have it in series. That also works. But that allows you to then just indiscriminately model time series, and it can represent a light curve properly. So that should really help you with these multiple light curve issues, for example. That could easily take care of that. Yeah.
Cool. Thank you.
Yeah, just Google his name, Mario Morvan, and it's Pi light curve torch thing. So yeah, hopefully that'll be useful.
Great.
If no one has any other question, I do have another question. So in the Himes 2021 paper, you said that one of the problem was that it wasn't maintaining the traditional Bayesian sampling, as in like it was still far from the Bayesian.
No, the
sampling.
Himes paper. So the Himes paper is just using a surrogate forward model, atmospheric model, and so they instead of trying to do the full backwards propagation from spectrum to parameter, they're like, no, we're using a traditional Bayesian sampling. We're just using a normal MCMC, and just the actual atmospheric model is a neural network.
Okay.
So their approach is fully Bayesian in that sense.
Okay, yeah, sorry, but like my question was, do you think that this is going to be, that the Bayesian statistics are still going to be the foundation for like deep learning and exoplanet characterization, or that there will be other statistical approaches that will come forward as well?
I think Bayesian, this normal Bayesian will be the norm and should be the norm. I mean, the field has started off with a maximum likelihood modeling and optimal estimation, and that's good if the signal to noise is extremely high. So in the planetary science, you're only doing optimal estimation, which is just, you find the best fit and that's it. And maybe a covariance matrix around that best fit, but that's it. That's fine for Mars. For exoplanets, the signal to noise and the resolution will always be such that I think, because we're always pushing the boundary, right? We're always going to look at smaller planets with worse signal to noise, that you need to formally take into account the noise of the data properly.
Yeah. Any other question from the attendees? Okay, well, if not, it's 5:05 for me, so wait, 12:05 for you. So I think we can, we'll close here. And if you have any other question, please feel free to email to email me, and I will pass on to Ingo, or to email Ingo directly if he's okay with that. And yes, thank you for attending. The next talk is on June 10th about the geochemical pattern of biochemistry, I think. So yeah, just watch the space coming on in the spans of the Exoplanet seminar series, and we look forward to seeing you again. And thank you again, Ingo, for accepting the invitation.
Brilliant, thanks for having me.
You're welcome. Bye. See you.
Thank you.
Thank you. Bye.
Thanks.